derivative formulas. This is page 2 of 2. So on the on the bottom of page 1 of our derivative notes, we we made a list of the functions that we've looked at so far, things like square root of x, and the derivatives, the derivative formulas that we were able to figure out for these. So our big goal now is we're hunting for formulas that we can use so that we don't have to continually use the first or the second definition of the derivative, right? So these are a couple of them. You have them on your notes on the other side here. All right. So if you look at the top side, there's a whole bunch of verbiage there in your notes that you should read through. But again, we're looking for patterns, and in particular, we're looking for the patterns in power functions, things like x to the 0, x to the first, x to the second. So we've already seen the pattern for x squared. So in example 2 on the back side of your notes, we're going to be looking for the pattern that's going on with x cubed. So let's actually just take a quick look at the x cubed function. So here's GeoGebra. I've got the x cubed function. Down here at the bottom we have the second definition of the derivative. When we make h smaller and smaller and smaller, here I've got an h of 1. This is my tangent line. I'm trying to figure out the derivative at this point here, the blue point. As I bring my h smaller and smaller and smaller, I get a better and better approximation of the derivative. When I get right on, when I get so that h is 0, there is no value. So I'm looking for something really close, and it's looking like at this point, blue point I'm looking at, my derivative is somewhere in the vicinity of 3.5 perhaps. So I'm putting this second derivative formula up here, just second definition formula of the derivative up here, just to remind you of that. What we're trying to do here for the x cubed function is we're trying to find, different GeoGebra sketch here, we're trying to find a pattern in the derivative. So what I have here in purple is this is the value of the function, and then right here this purple dotted line is the tangent at that value. So if I can find the slope of that tangent, then I have the derivative, and that's what this red point here is. And you'll notice as I move the value of the function, if I'm moving along the function, the derivative is changing. I have a very steep derivative here. The derivative is getting to be less and less steep. When I get right down here at 0, 0, the derivative is 0. And then as I go to the left of the y-axis, my derivative again gets steeper and steeper, and it is also positive. So it looks as if there's a pattern in the derivatives. And that's what we're hunting for. We're hunting for the formula that'll tell us what this pattern in the derivatives is. All right, so let me see if I can do this here quickly for you. I'm going to put trace on this point, and we're going to watch to see what this pattern in the derivatives is. And you notice here as I'm going through, my derivative is leaving sort of a trail behind it. So the red is the pattern of the derivatives as I'm going along my function. As I'm going along my function, that's the purple. And it sure looks like when I take x cubed that I'm going to get something in the vicinity of an x squared function for the derivative. Right? So the hypothesis, get back here, is that if we have a function that is x cubed, the hypothesis would be that its derivative would be something in the order of x squared. All right, so we're going to go quickly through and actually crank through the second definition of the derivative and actually prove that that is indeed the case. Right? So first off, the second derivative formula. So I'm now working on the back side of your notes on example 2. And we'll see if we can go through this quickly for you. So first off, we lay down the second definition of the derivative. So there it is, the second definition of the derivative, and over here in red is, just as a reminder, the function that we're looking at. So now I'm going to take the x cubed and I'm going to use that as my function and plug in x plus h into the function, plug in x into the function, and rewrite this, which then looks like this. And now I'm going to take this x plus h and I'm going to cube this. If you remember about squaring and cubing, there's a pattern to taking a binomial, squaring it, cubing it, raising it to the fourth, raising it to the fifth, that involves the Pascal's triangle. So I'm going to over here write, over on the right, we'll put out Pascal's triangle to help us with the coefficients of this. Alright, so here's what we've got in the blue. I've expanded the x plus h cubed, and we got this pattern where the variables excuse me, are x cubed and then x squared and then x to the 0, and then the h's are h to the 0, h to the first, h squared, h cubed, and then the coefficients come from Pascal's triangle, which I've done over here. And if you remember, Pascal's triangle, out on the edges of the triangle are the ones, and then the numbers on the inside are the sum of the two numbers up above. So using Pascal's triangle here, we can, the pattern helps us figure out what the coefficients of the four terms of the expansion of x plus h cubed. So here in the fourth line, we get 1, 3, 3, 1. The coefficients are 1, 3, 3, 1. So now we've expanded all of that out, and we can start simplifying it. And the x cubed here, 1x cubed, we subtract at the back end 1x cubed. So those go away. And then we have 3x squared h, 3x h squared, 1h cubed, and we notice that each one of these has an h in it, so I will rewrite this so it looks like this, h, and then we're left with here a 3h squared plus 3x h plus h squared, all divided by h. We end up then with an h in the numerator and h in the denominator. These reduce to 1, which then leaves us with this. And what we notice is that as h approaches 0, this term here is going to approach 0, and this term will also approach 0. So what we end up with is that the limit as h approaches 0 is 3x squared. And just to remind ourselves, this is the derivative of this function up here, the x cubed function. Its derivative, we've just proven, is 3x squared. Where we go down here from next? Next, we're looking at example 3. And here's how I want to go through example 3. I've got another GeoGebra sketch here. And in example 3, we're looking at the x squared function. So here is the x squared function in black. And what we want to do is we want to consider what's going on with the 4x squared function. All right, so in example 3, we're now going to start looking at what's going on with the coefficients. We saw, or we're starting to see this pattern where the exponent of my function, when we look at the derivative, gets knocked down by 1. Right? So an x cubed function has a derivative function which is x squared. And we now want to start looking at what's going on with the coefficients. Right? So here's my x squared function. How does the derivative change? How does this derivative function change if instead of having 1x squared I have, say, 2x squared? Right? 2x squared. Or if I have 3x squared, or if I have 4x squared, or if I have... Right? So what's going on with this pattern in our derivative functions when the k, the coefficient in front of our power, is changing? Right, so let's put this back at k equals 1. I've got here back to my second definition of the derivative, right? So the limit as h approaches 0, and I've got my x, I think, on 1, and as h gets closer and closer and closer to 0, we find that the derivative is somewhere in the vicinity of 2. And in fact, it is exactly 2. All right, so I'm not exactly 2 here because h isn't exactly 0. Again, I'm doing my approximation. The red line is the tangent. Excuse me, is the secant. It is not the tangent, it is the secant. So I have an approximation. So what we want to look at is, well, what's going to happen when we change the k? And as we change k, if k is 2, right, what's going on in the function is the function rises twice as quickly. Right? So for every x you put in, then you double the output, basically. So this thing is twice as steep. And if k is equal to 2, notice that my derivative, which was approximately 2, is now approximately 4. It's twice as steep. If my k is 3, my derivative, which was 2, is now 6. So it is approximately 3 times as steep. And then if k is 4, here I am, my derivative is approximately 4 times as steep. So that being, noticing that, we can fill in our notes here pretty quickly. So for example 3, if we're talking about the x squared, so if f of x is equal to x squared, then the derivative at 1 is equal to 2. The derivative at 2 is equal to 4. And in general, the derivative at 2x, the derivative at x, ahead of myself here, the derivative at x is equal to 2x. And then if we look at, this is what we're putting down in our notes, if our original function is, 4x squared, well, the derivative at 1 of the 4x squared is going to be 4 times as steep as at the original function. So this is going to be 8. The derivative when x is 2 is going to be 4 times as steep as it was over here, which is 16. And then in general, the derivative of the 4x squared function is going to be 8 x. And this is 4 times that. All right. So the fact that we get from all of this is that if you take a function and multiply it by k, and then we take, I'll write it this way, a little apostrophe there to say the derivative. So if we take the derivative of this function, which has been multiplied by k, it is equal to the derivative of the original function, which gets multiplied by k. And then quickly finishing up the notes, example 4, you'll see that, excuse me, the, we'll do this in orange. If the original function is 6x cubed, then the derivative is going to be, we've got this 3x squared, we just saw that, is the derivative of the x cubed, and then it's going to be 6 times as steep, so it would be 6 times that, or 18x squared. And then the last one, if our original function is 1/2 x squared, 1/2 x squared, well, the derivative of that is going to be x, right? So the derivative of x squared we found was, is 2x, and then we're going to be half as steep as that, so it'd be 1/2 times 2, which is simply going to be x. And we are now done with our second page of notes.